Hello there, this is Miss April, and if you're watching this, you're likely in my Algebra 1 class. So, this is the workbook that we'll be using, and we're going to cover chapters 1 and 2 in this video. All right, let's get started. So, chapter 1 is all about number theory, and so we're going to break down numbers into first real numbers or imaginary. Now you will not be doing any computations with imaginary numbers in this class. Okay, we're going to focus on the real, but just so you know that they exist, right? We have this little imaginary number that we do use in more advanced algebra. All right, helps us to remove that negative outside of the negative that's stuck inside of a Radican here, right? So we can do anyway. So real numbers, focusing on real numbers. So there are two main categories of real numbers. We have the rational ones. Yes, you can reason with these. And then we have the irrational ones. Don't even get me started. Right? Okay, so the irrational numbers are things like pi. Will it ever end? I don't know. So maybe we have like a negative square root of 7, right? That is a long string of decimal numbers. They can't be expressed. So rational numbers cannot be expressed as the quotient of two integers, right? There's just no way for them to be anything other than this long string of decimals. You go ahead and try to put that in your calculator and see what you get with numbers like this, okay? All right, so rational numbers, the ones we deal with most of the time, can be broken down. But in a broad sense, rational numbers can include fractions of numbers expressed as a fraction or as a decimal. It can be a mixed number, and maybe even like a repeating decimal, right? Things like that. And of course, whole numbers. But within the rational numbers, we have a grouping that we call integers. Now, integers will include your -3, -2, -1, 0, 1, 2, 3, and then infinitely in either direction on the number line. So, usually when we talk about integers mathematically, that's when I'm giving you a problem like -2 minus a -5. So you're dealing with integer calculations. Okay, now within integers, we have another classification. It's called whole numbers. Okay, now our whole numbers include 0, 1, 2, 3, and so forth. Within the classification of those whole numbers, notice that whole numbers do include 0, but we have something called natural number, and sometimes it's called a counting number, which might be easier to remember because these are the numbers we use to count. Do you say, I have 0, 1, 2, 3 pencils, right? That would mess you up. Don't do that. So we count starting with 1, 2, 3, and it goes on, right? So those are our natural numbers and counting numbers. Now these are sort of nested, and what we have to think about is that integers are also rational and real. Whole numbers are included in the integers, rational numbers and real. Natural numbers are also whole, integer, rational, and real numbers. However, not all whole numbers, specifically I speak of 0, are natural numbers. Not all integers are natural numbers, right? Because there are no negative numbers in counting or natural numbers. All right, hope that makes sense. In addition to this, we want to think about rational and irrational roots. If n is a positive integer and an nth root of x is a number, that when we factor n times gives x, the number's nth power. So, for example, we have a notation that looks like this, right? The nth root, where we don't write anything like this, we usually don't write a 2, but if the radical's there by itself, then we know that it is the square root, or we could say the second root of x. And on a practical note, if we have something that looks like this, then we know we're asking ourselves what times that very same number gives us a 16. So let's look at the vocabulary. This bar, this funny little bar here, that is a radicand. And the number within the radicand is the base. The number that is the root is, well, that's the index. There are certain truths about these radicals that we need to understand. If we have a negative 16 under here, well, that's not possible, right? We say this is not real. And we deal with it using one of these imaginary numbers we spoke about earlier. So we have a number like this. Well, it's irrational. The reason why it's irrational is because you can't square that perfectly. When we're looking at cube roots, we can have a negative under the radicand because this is some number times itself 3 times. And we do know the rule that when you have a negative times a negative times a negative, we can have a negative answer. And we will, right? Because we see that negative 2 times negative 2 times negative 2 does give us the negative 8. this would be a positive 4 times a negative 2 gives us a negative 8. It's also okay to have a negative outside the radicand for any situation, whether it's squared or cubed or you're looking at the 5th root. That's fine. It's applied afterwards, right? We have the negative still out there, but the square root of 16 is 4. Just remember that if your index is an even number, you may not have a negative on the inside of that radicand. It's not real. Okay. If it's an odd number, you can have a negative. That checks. Being that it's an odd number, it'll produce a negative answer. Remember the inverse rule of this when we're multiplying integers. We count the number of negatives. 1, 2, 3. We have 3 negatives, and that's odd. That means that our answer will be negative. So if we have an even number of negatives that we're multiplying, then we'll always have a positive answer. All right, moving on. In chapter 2, we're looking at properties of real numbers. And there are a lot of different properties that I think are important to understand and memorize. We have properties of addition and properties of multiplication. We do not have any properties of division or subtraction. And you'll see why. So let's look at the commutative property. So the commutative property of addition allows us to take two numbers and demonstrate the fact that it doesn't matter which order we put them in. We'll have the same answer. The same is true for the multiplication. Times 3 will equal the same thing as 3 times 2. However, these do not work for subtraction. 2 minus 3 does not equal 3 minus 2. 2 divided by 3 does not equal 3 divided by 2. They do not work for subtraction or division. Next, we have the associative property. And sometimes people confuse the commutative property and the associative property. But think about this. Commutative, you're beginning with the 2 digits, and you're flipping them. The associative property gives us a rule that when we have 3 or more numbers, and in addition, if I were to say 2 plus 3 plus 1, it's not about changing the order. It's about which ones you associate together first. So I can add 2 plus 3, which gives me 5, and then add 5 plus 1. Or I can add 3 plus 1, which gives me 4. Then add 2. So it doesn't matter which ones of a given series of numbers that you add together first, because if it's all addition, it's associative. Multiplication holds the same rule. Two times 3 times 5 equals 3 times 5. Remember, the order doesn't change, just which numbers you decide to multiply together first. I could multiply the 2 and the 5 together first. It doesn't matter because it's all multiplication, and that makes it associative. Identity properties. See here, a lot of times the clue is in the root of the word. Identity, think identical. So for addition, what I'm thinking is, if I begin with a 5, and of course I'm adding something, what can I add that will give me the identical number? Well, when we're adding, that number is 0. That's the identity property. When we multiply, if I start with a 5, and I want to multiply it by something, and I want to end up with a 5, what will give me that identical number? That would be a 1. That's the identity property of multiplication. Easy. Now, inverse properties. Inverse properties of addition. I want to think, if I begin with a number and I'm adding, what will give me 0? And that would be a -5. Think inverse kind of undoes the addition. My goal is to equal 0 when I'm adding in the inverse property. If I'm multiplying, and I start with a 5, my goal is to find a number that will give me 1. The only way that's going to happen is if I have a 1/5, because we multiply straight across. And essentially, we first wind up with 5/5, which is 1. Let's look at the distributive property. Then there's a key in the name here, distribute. When we distribute something, we give it fairly to each person involved. So you have a number, and this governs multiplication, right? So we have 3, and let's do 5 plus 2. We need to distribute that 3 first to the 5, and then to the 2. We know it's multiplication because of the parentheses, and there's no other operation between the 3 and the parentheses. So that tells us we're multiplying that 3 times anything inside of that parentheses. So to demonstrate this property, we need to show a 3 times a 5 plus this operation carries over, a 3 times a 2. Now, if I had given you this problem, you might have just added 5 and 2 and then multiplied it, which is fine. It's really most applicable in algebra like this. You can't add x and y, but what you can do is distribute that 3 to each term let's look at the zero factor property. So 0 is a key and factor is a key. So if any number, real number, is multiplied by 0, what's the product? 5 times 0. It always equals 0. It doesn't matter how big that number is. Times 0 equals 0. You will always have 0. Easy. So that concludes lesson or chapter 1 and 2. Come back and see me for chapter 3.